So tonight we're going to be focused on en route flight. En route flight means after you depart an airport, you go en route at a cruise altitude, and then you go down and start to arrive into an airport. So we get depart, en route, and arrival. We're talking about the en route phase when you're at altitude in cruise. And so we're going to talk about some of the key navigation tools that we use for en route flight. First thing we'll talk about is pilotage, then time, topography. Topography is associated with the land and the shape of the land, the mountains, the hills, the water. Dead reckoning, how we actually determine where we'll be in some amount of time based on a certain speed that we're going. We'll talk about using this tool here, E6B, for plotting courses, dealing with magnetic variation, magnetic deviation, compass deviation. We'll talk about wind and how it affects the route of flight. And again, then we're going to watch a few short videos that I've done on how to use this thing. And our lesson starting next Monday night is the first of 2 nights on cross-country flight planning. And we, as part of a private pilot, you need to have 3 hours of cross-country flight planning where you actually fly with an instructor on a cross-country flight. What's the definition of a cross-country flight? You go at least 50 nautical miles and land at another airport from your destination port. So if we left Laconia and went out to like an airport that was 57 miles away and landed there, that would be a cross-country flight and then return back. And so that's the definition of a cross-country flight. And when we go out on one of these cross-country flights, there's a lot of planning we do. We do a weight and balance calculation, which I think you guys have already covered already. We create a navigation log, where we find waypoints or checkpoints along the way, and we have to determine what heading we're going to fly on the plane, and we have to base it off what we have for wind correction, what we have for magnetic compass variation, etc. So we're going to talk about all those things, and the last part is we'll touch upon airspace again. I think we've already covered a little bit about that. So pilotage is use of visible landmarks to maintain a desired course. So when we go on one of these cross-country flights, let's say we leave this airport and we normally go often to Auburn, Lewiston, Maine, we're looking outside the plane to see if we see things out of the plane that look like on our sectional chart. This is a sectional chart called the New York sectional chart, but it covers a lot of the Boston area. And I don't know if you're going to see this, I'll just show it here for a second. Right there, that's a New York sectional chart. And what we'll do next week, and it would be good, Brian, if you can attend next week, because a lot of lab work, if you will, that we do in class. We'll go on these trips, and we'll have to find various spots along our route of flight, like mountains, lakes, ponds, towers, etc. And those become landmarks that we're looking for when we're flying. And they help us to maintain our desired course. The VFR sectional chart, again, this is the VFR sectional chart. They come out every 56 days, they update them, and there's about roughly maybe I think 50 of them that make up the entire United States. This little picture right here, you can see it's kind of a grid of the United States. Every one of those little blocks represents an individual sectional chart. Then there's something called the VFR terminal area chart for Class B airplanes. So for Logan, which is represented here by the concentric blue lines and the big yellow area of the city lights of Boston, there are VFR terminal area charts for just the Boston area. And as a result of that, they can zoom in and see a lot more detail around the Boston area. So it covers a lot smaller area, but provides more detail in that smaller area. And then on the flip side, we have world aeronautical charts for moderately fast airplanes. Normally VFR sectionals, terminal area charts are for slower speed aircraft. World aeronautical charts are for faster planes. And they cover a much, much bigger graphical area. So I forget how many there are in the world, but there's a lot fewer of them, and there's a lot less detail on them. And for the most part, you won't even be involved in them as your private pilot through your commercial licenses with World Aeronautical Charts. Longitudinal, let's see if I get a, let me get up here for a second. Pointers. Longitudinal lines on the world globe are these vertical lines that go from the North Pole to the South Pole. And they're also known as meridian lines. And you notice there's one called the prime meridian line that goes through Greenwich, England. This is basically where back in the old sailing days in England, as a big sailing industry, basically time was made or distances and stuff were made relative to Greenwich, England. So the prime meridian line represents 0 degrees and it passes again through Greenwich, England. Brian, are you still there?
Yes, I am.
Okay, good. Latitude. These are the horizontal lines that run parallel to the Earth. And the equator represents the 0 degree line. And then it's like 30 degrees. And then as we get up toward, let's say, New Hampshire, it's like the 43rd parallel. And eventually, this is the 60 degrees, and eventually make it up right up to the top, to the North Pole. And I want to highlight, this is the true North Pole. It's not the magnetic North Pole. That is quite a bit distance away, like 1,300 nautical miles away from the magnetic North Pole. So we got true North Pole and true South Pole. And again, the equator, equidistant from the poles, the North Pole and the South Pole. It's an imaginary circle. But just as a side note, I believe if you were to try to flush a toilet on this side of the equator, it'll rotate one way. And if you go on the South Pole, it'll rotate the opposite way. Tidbit. Again, more terms used in navigation. We have compass heading. So we have a magnetic compass in the plane. That's if we're flying relative to the magnetic North Pole, which, as I just said, is not coincident with the true North Pole. And it can vary. Magnetic deviation is the magnetic anomaly that affects the compass. So there is things, as I said, the North Pole and the true North Pole, magnetic North Pole, the true North Pole don't line up with each other. So you could get some anomalies when you're reading the compass from that perspective, but also associated with metal in the plane, radios, and other types of electromagnetic or metal interference can cause the compass to have some variation. Ground speed. Let me just pull my little plane up here for a second. So ground speed is associated with how fast we're going across the ground, the surface of the ground. It's different than the airspeed. If I have a strong headwind, I may be reading 90 knots on the indicated airspeed in the plane, but my ground speed may only be going 60 knots. So again, if I'm going 90 knots through the air and there's a 30 knot headwind, my net speed across the ground is only 60 knots. On the other hand, I could be going 90 knots airspeed, but have 120, have a 30 knot tailwind. So now I'm going 120 knots across the ground, and that's called ground speed. And we care about ground speed because when we're trying to make these trips, these cross-country flights, we're seeing how fast we can get across the ground. And so it's not just associated with the airspeed, but also whether or not we get a headwind or a tailwind, or some version of that. The magnetic course is the true course corrected for the magnetic variation. Again, these are associated with the fact that the North Pole is not in line with the magnetic North Pole. We have magnetic heading. That is the course, the magnetic course corrected for wind direction and speed. So if we want to go there, but the wind's coming from me to the left, if we just try to go to that point here, the wind is going to be pushing us this way. So we're going to have to turn on a magnetic course heading corrected for wind so that we basically fly kind of this weird crab heading to get to this point over here that we wanted to go to. Otherwise, if we don't crab, we're just going to get drifted off to the side. Pressure altitude. You'll hear all these different types of altitude, but pressure altitude is the height above what they call the standard datum plane, which is a theoretical level where the air pressure equals 29.92 inches of mercury at sea level. I'm going to try to draw on this whiteboard here for a second. Tell me if you can see this, Brian, or not.
Nope, I can see it.
Okay, so this is the mountain, and this is the ocean. Okay, when we're sitting here at sea level, the international body came up, standards body came up with a standard datum plane for everything to be based on relative to altitudes that you're flying or how aircraft engines perform and so on. And at sea level, it's considered a standard datum plane or standard atmosphere when the barometric pressure reads 29.92 inches and temperature reads 15 degrees Celsius or 59 degrees Fahrenheit. So the standard datum plane or standard atmosphere is when you're sitting at the beach and the pressure equals 29.92 inches of mercury and the air temperature is 59 degrees Fahrenheit or 15 degrees Celsius. And why do we care? Well, if you look, you'll see this when we start doing this work next week. There's all of these performance charts based on pressure altitude, but followed by knowing what the temperature is. So we have to know what pressure altitude we're departing from and what pressure altitude we're flying at en route in order, and then factoring in temperature to really know how the plane's going to perform. The other thing too is you'll hear us say when we're flying this kind of low level altitude that we just put in the barometric pressure, the altimeter reading that we hear when we listen over the radio. When you're on an airliner flying at 35,000 feet, they're all flying at something called the pressure altitude with their barometric pressure, or the altimeter, I should say, set to 29.92. Why is that? Well, they want to have everybody in the same playing field. If you have planes flying 500 miles an hour going across the country, they can't afford or have the time to be sitting there changing their altimeter setting every time they're passing over a different city and there's a different pressure, low pressure, high pressure, whatever. So at 18,000 feet and above, every pilot will set their altimeter to 29.92 inches. And even though that may not translate into that day of being literally 18,000 feet above the ground, what it means is there's equal separation. So this guy is flying at, let's say, 30,000 feet, and air traffic says, I want you flying at 32,000 feet. If both guys set their altimeters for 29.92, we know there'll be at least 2,000 feet separation between them. They may not be at 18,000 or 30,000 feet or 32,000 feet. They might be at 31,000 and 33,000, but at least they've got the separation. So that's why we care about pressure altitude. It affects the performance of an aircraft, and it also assists when you're flying at higher altitudes above 18,000 feet. And a private pilot can do that if they have an instrument rating flying an instrument flight plans. Density altitude is one step further. You take the pressure altitude that you come with and you factor in the non-standard temperature. So you could have a day where the pressure at sea level is 29.92 inches, but instead of being 15 degrees C, it might be 30 degrees Celsius. It might be a really, really hot day. And so the aircraft is now going to perform quite poorly because of that very, very hot weather. Even though the barometric pressure might have been perfect, 29.92, the temperature is so high that the aircraft's going to perform quite poorly. And I'm going to draw another picture on the board here of density altitude. I don't know if I have a good picture of it. I hope I do, but I don't think I have this picture. If we just draw this one column of air, and this is sea level right here, and it's a perfect day, 29.92 inches and 15 degrees Celsius. At 1,000 feet, you're going to have, this is 1,000 feet, you're going to have 28.92 inches, and you're going to have a temperature of 13 degrees Celsius. At 2,000 feet, it's going to be 27 0.92, and it's going to be 11 degrees Celsius. And so as you go up the air stack. And part of the reason for that is the air molecules are really dense down here, but they start getting fewer between as you go higher and higher up in altitude. Why? Because of gravity. Okay, there's less gravity, there's going to be less molecules up here. And so if we say this is 2,000 feet, and assign it 2,000 foot density altitude, and this is the 1,000. If we're told that the density altitude on the beach that day is 2,000 feet, it's going to be as if the plane is performing as if it's 2,000 feet up in the air. It's just going to be thinner air, weaker air, and so you're not going to get as much performance out of the engine. The wings aren't going to have as much lift. So that's what density altitude is about. Whoops. All right, let me get my mouse in the right direction. I struggle with this. There we go. So again, standard temperature and pressure for standard atmosphere is 29.92 inches of mercury at 15 degrees Celsius. I should have said at sea level. Indicated airspeed. As I mentioned earlier, this plane flying along and it says 90 knots on the indicated airspeed. That's not the ground speed, that's just the indicated airspeed that the plane is seeing at the moment. Then we have something called calibrated airspeed, indicated airspeed corrected for instrument and installation error. So we see indicated at 90, but the plane may actually be flying something different because of where the pitot tube is, or how its relationship to the wind, or how the pitot tube or even the instrument inside the plane are mounted inside the plane. So these are instrument installation errors, and it can actually be position errors too. And then true airspeed, calibrated airspeed corrected for density, altitude, and actual airspeed. So let's say this plane is going 90 knots through the air, indicated. Well, think of it this way. When you're down low at 500 feet above the ground, there's lots of air molecules here, okay? And they're all going into the pitot tube where all the air gets kind of rammed air in, and it shows 90 here. What do you think the real true airspeed is like when you're way up high and it's still showing 90 knots? Do you think the true airspeed is going to be a lot faster or slower than the indicated airspeed when you're really high? Any thoughts? Faster? What do you guys think? Was that yes?
Yeah.
Faster? And yourself? Faster, yes. Why? Because if I'm going to register 90 knots here, I must actually be going faster to, let's say, scoop in all those air molecules that are much fewer apart way up here at higher altitude than down here. Easy to collect them down here. There's tons of air molecules really low here. And if it's saying 90, great. But when I get up here and they're further apart, I better be going faster if I'm going to see. I'm going to have to go faster to show this the same 90 knots here. So the general rule of thumb is every 1,000 feet you go up in altitude, their true airspeed is about 2% faster than the indicated airspeed. Again, aeronautical charts, roadmap for VFR pilots. That's what these sectional charts are. Topographical information. They do show some information about field elevations or elevations of the area. These big blue numbers you see here throughout the map, they're called maximum elevation figures. They tell you what the highest object is. It could be the mountain, it could be a tower on top of a mountain in the sector that it's encased in. They also, again, provide information about how the mountains are, and all that information can be made available on an avionics system. So you get this kind of green, yellow, or red type imagery on the screen to see how close you are to the mountains as you're flying over for the terrain. Navigational aids, we're going to talk about those in a bit. Frequencies to dial in those navigational aids, and we'll talk more about airspace. Reference legends on a sectional. This is a legend, and if you were going to go for your check ride to be a pilot today, you better know everything on this legend. Yes, you could sit there and say, oh yeah, I don't know what this vignette purple means, and I can come over here and figure it out. But you're only going to get somebody passes by the examiner where you keep looking at the legend. So it's something you need to really study, even for the written test. to pass the written test. You have to know that. Sectional charts. This is kind of nuance that you don't need to worry too much about, but its scale is 1 inch represents 500,000 inches, or 1 inch equals 6.86 nautical miles. So the scale is 1 to half a million, but it means really is 1 inch on here. 1 by 1 equals 6.86 by 6.86 nautical miles. Revised semi-annually. No, I don't know. That's a typo. I should have fixed that. It's every 56 days. And the same with the terminal charts. As I said, they're like a zoomed in view of a particular airport, such as, let's say, Logan or Chicago or something. And it gives you a much better resolution. 1 inch equals 3.43 nautical miles. Yeah, as I said here, VFR and terminal charts every 56 days are updated. What can change? Constantly things changing. New obstructions, new cell phone towers, new runway that have been installed, frequency changes, just almost anything you can imagine can be happening, and it happens quite regularly on these maps. So that's why I have to update them so often. Tools like ForeFlight or Garmin Pilot. I have ForeFlight on my iPhone or my iPad, and it basically gives me these sectional charts. And that's what you see here. It's exactly the same sectional there, except it can do it over the entire country. And it's up to date and accurate. And there's no more having to buy these paper charts and update them every 56 days. As a side note, as a matter of fact, you can't even have these in your plane and hint you that you're using them for navigation. Right here it says expired. It's not for navigation use. I read on here. Because as soon as they expire, if the FAA number stops, does a ramp check on your plane view and sees you're flying around these in here, and then you don't have ForeFlight or something else that's current, you're going to get in trouble if you're using old stuff. So tools like ForeFlight eliminate that. So now we're going to go a little bit deeper now into pilotage and dead reckoning. Pilotage is a navigation using the sectional chart, flying from one visual landmark to another. The landmarks chosen should be easy to spot from altitude, and usually no more than about 15 nautical miles in between each mark. You can't see it on the sectional ad here unless you're like staring over it, but you'll see pencil marks on airport A to airport B, and we'll put little vertical tick marks or perpendicular tick marks along the route, and those represent landmarks that we've chosen that we can easily see when we're flying, like ponds, like lakes, like mountains, like city lights, like very tall lit up towers, etc. Wind turbines are easy to see. So we have pilotage portion, looking outside the plane and then comparing it to what we see in the chart. And then we have something called dead reckoning. Again, this is about navigating solely by and understanding what the wind, your ground speed is, the distance that you're trying to travel, and your time calculations. If there's one simple equation in physics you probably ever want to learn, didn't you guys take physics? Okay. So there's something called S equals VT. Do you guys know what that means? What does it equal? What does it stand for?
Speed equals velocity times time.
No, not speed. S is for distance.
Distance.
Distance equals velocity times time. Okay, so that's what dead reckoning is about. If we know our distance between points and we know our velocity or ground speed that we're going, we can see it. We can figure out how long it's going to take us to get somewhere. Okay, that's what that's about. That's what dead reckoning is about. So I'm going to go from point A to point B. I'm going to be going at this ground speed, and I'm going to, I know the distance between those points. It should take me this amount of time. If I'm not there in that period of time, well, something's wrong. Maybe I didn't correct the wind. Maybe I'm off course, etc. And if we find out when we're flying a route that it's taking us longer to get there than we thought, we may need to make adjustments. We may have to make adjustments, say we're not going to get to our destination for a little bit longer. Or we might have to go faster if we want to shorten our time. So plotting courses. Let's see. This is a plotter. you guys got this when you got this course, and if you don't have them tonight, you definitely want to have them next week, okay? Plotters in 6 weeks, have them, and you have a sectional chart like this. Bring them because you're gonna be, again, doing kind of a lab. And it's gonna keep you busy. So plotting a course, you need to choose your departure airport and your arrival airport. Again, the definition of a cross-country flight is you gotta be at least 50 nautical miles away from your departure airport. Select route with locations that allow for refueling. It's always a good idea, even if you have full tanks and you have plenty of fuel to get to the flight, to go along a route that will set you up that if you needed to get fuel, you can easily stop, and land and get fuel. They should also be used, those refueling airports, as possible alternates. Today was a prime example. I was out flying a few hours ago. Rain and storm weather was coming through here, and we went out towards Sanford. We're just in air work, but I went in that direction. It was crystal clear, and if we had to get down or land relatively quickly, I could go land in Sanford, then trying to come back in through a heavy downpour. Choose airports nearest to the charted route. So we'll get to it a little bit later, but you might want to choose a path that'll take you close to potential refueling spots, again, within 15 nautical miles. So I've got a number of videos I put out on this topic. We're going to start by looking at the first one, which is on how to plot a course on a sectional using this plotter. Now, this is where it's going to get interesting. Brian, you tell me if you can't hear anything that I try to play here.
Will do.
Let's see if I can get this. Maybe I have to get out a pointer. Oh, doggone it. How do I get out the pointer options? Automatic. Oh, for God's sakes. Okay, so. All right, bear with me as I figure this game out. Might take me a minute just to get myself figured out here. I struggle with this part. There we go.
Here's how
This is at 38 seconds.
you can't always plan when you'll need a gun. Rational gun owners carry not because it's a weapon, but because it's
Leave them below. So Brian, can you see my screen with the video about to play? Brian, you still there?
Yeah. So which screen, you're playing it on your computer.
Yes. Can you see it though?
If I click on that, yeah, I can't see it full screen, but I can see it.
Well, I'm about to make it full screen. You tell me if you see it. How's that?
Well, what I'm seeing is my full screen thing is still the one on top, plotting courses.
Okay, I think I know what I have to do. I somehow have to kind of like slide. This is where I struggle a little bit. Give me a minute.
Yeah, in the past, I think you can kind of drag it up to the top one.
Yeah, that's what I'm trying to do. Certain way. Oh, here we go. Here we go. Feels like I only halfway dragged it. Almost there. I have to watch another ad.
If you're finally ready to take a trip without the kids,
So follow along. In this exercise is part of cross-country flight planning from Laconia. I think I got the wrong one. Give me a minute. I'll figure this out sooner or later.
You can check on the right-hand side if it's in there, full list.
Oh, yeah, now I can't remember what, yes, it sure is in the list. How can I see my own slides? Here we go, I'll just take that. Plotting course. plotting course. Okay, so go back to that. There it is. All right. Actually, how do you use plotter? Yeah, this is it. There we go. All right, Brian, can you see that fully now?
Yep.
First thing we want to do is place our plotter along the course that we plan to fly. We're going to fly between Laconia Airport here and Auburn Lewiston Airport up here. So I'm going to put my plotter in between the 2 points. I'm going to take a pencil and draw a very thick line so it's very legible to see, particularly in the air when you're flying. So what we really want to be able to use this for is pilotage and dead reckoning. Next, we want to measure the distance between the two airports using the plotter. I mean, what we want to really be careful about when we use the plotter is make sure on the sectional side in measuring in nautical miles, because that's the way the chart we have here is a sectional chart and it's measuring nautical miles. So make sure you're in the right ruler scale. If you turn this over, you would see statute miles here. You also see some references to the world area chart. You may also see the terminal area chart ruler scales. So you want to make sure you're using the proper scale, ruler scale for the chart that you're measuring. In this case, we're measuring a sectional chart. We want it in nautical miles. So once we've done that, we'll place the plotter down across the line. We'll put the start point of the ruler on the center of the airport, and we'll measure to the center of the airport up on this end at our destination. And if we look at that, it reads 55, 56, 57 nautical miles between Laconia Airport and Auburn Lewiston in this straight plotted course line. Now we want to determine the true heading between the two airports. And to do that, we're going to use the protractor side of the navigation plotter, and we're going to pay attention to this little grommet hole here. And what we're going to do is take the straight edge line associated with the protractor side and line it up along the course that we've drawn on the sectional chart. Then we're going to slide the plotter until the grommet is lined up right over one of the longitudinal lines that runs true north, such that that line intersects the grommet and intersects our course that we've just marked. And once we've done that, we can then determine our true heading that we're flying. Well, this vertical line is true north, so that's 0 degrees. And so we're going to basically measure this angle difference. If we look here, we've got 10, 20, 30, 40, 50, you see 60. We're slightly less than that, so it's about 59. So our true course heading is 59 degrees for this flight. There'll be sometimes when we plot a course that it doesn't cross longitudinal lines, but it does cross a latitude line. So in this particular type of situation, all right, so that's basically how we use a plotter to find out what our true course is relative to the North Pole. But that doesn't mean anything about, that's the way we're going to actually turn the plane and fly to. We have to factor in wind and magnetic variation. So let me see if I can get back to my slides real quick. Oh, that was easy. Okay. Taking in en route cruise altitude. The next thing we have to think about is we got this route up to Auburn Lewiston, Maine from this airport, and we got to figure out, what altitude do we fly at to be safe? And what we care about is that we're going to fly at a high enough altitude that we don't bang into any mountains. And you see these numbers here, these big blue numbers. That means maximum elevation figure. It means somewhere in this grid here, there's something that's close to 4,600 feet tall. Basically multiply these numbers by 100. Something here, 2,700 feet, something here, 2,500 feet, something here, 2,200 feet. Well, as a result of this, we know that we probably want an altitude that's going to protect us safely from banging into mountains as we go through this region. I can tell you right here, there's something 4,200 feet tall. And so that's probably why they made this 4,600. So we're going to want to fly an altitude close to 1,000 feet above, minimum above the highest maximum elevation figure we see along our route of flight. That's part one. The second part of this is we have to fly at an altitude defined by the FAA is a route that is associated with VFR pilots flying in a heading from either 0 to 179 or from 180 degrees to 360 degrees. So if we were going to fly this route and we have to fly to the northeast, which we know is a heading between 0 and 179, we're going to fly an odd altitude like 3,500, 5,500, 7,500, etc., plus another plus that 500 feet. So odd altitude plus 500. So that would be like 3,500, 5,500, etc. Based on this, what do you think would be a safe altitude for us to go on this cross-country flight? Of those three altitudes that I pick here as an option, which one do you think would be the right move to fly? You got three choices. 5,500, yeah. If we flew at 3,500, we're basically 1,100 feet below this. And if we got lost along a route or something, we could bang into this mountain. Yeah, it's up here, but you could imagine how easy you can get lost and when you're going 100 miles an hour or 100 knots, it can get that direction very quickly. 7,500 would work as well. Gives you more altitude. Altitude's one of your good friends, along with fuel, runway in front of you, and airspeed. But it's not necessary. We could fly at 5,500 and still be very safe. Even though it's only 900 feet above that, it's safe enough. I wouldn't go much lower than that. If it was 700 or 800, I would probably say, nah, I don't know if I want to do that. But 5,500 is a good altitude to go. If we're flying east to west, and it was somewhere between a 180 to 359 heading, we would fly an even altitude plus 500, like 4,500, 6,500, 8,500. So let's say we're coming back from Auburn, West Domain. What altitude do you think we'd want to fly back at? 6,500, yep. Again, 4,500 would be 100 feet below the highest obstacle. They said there, 8,500s. I don't want to say it's a waste of fuel, but it's probably excessive. So pick a cruise altitude that is approximately 1,000 feet or higher over the highest max elevation figure along the route. And again, those big blue numbers are the max elevation figure. Next thing we're going to talk about, time. It's measured in relationship to the rotation of the Earth. There's 24 time zones around the Earth. Each time zone is 15 degrees of longitudinal width. And first zone centered on the meridian is Greenwich, England. So remember that picture of the globe, and you had a longitudinal prime meridian going from the North Pole to the South Pole. Every 15 degrees represents a new time zone. Okay, 15 times, I guess 24 is 360 degrees around the Earth. You'll hear people talk about Zulu time, also known as UTC time, also known as GMT time, Greenwich Mean Time. And depending where you are in the world, you would have a different, I'll call it fudge factor for what time zone you're on. So for example, right now, this might not be a good time to do it. It makes it more complicated. We'll make it easy. The best way to do this is whatever the local time is, put it in military time. Are you familiar with what military time is? Like 100, 1,300 hours means like 1 o'clock. Yeah, 1843. So if you can take your local time, put it into military time, and then add what I'll call a fudge factor to that. And it depends where you are around the globe. But here in the East Coast, during daylight saving time, we'd add 4 to that. So if it was 1,300 1,300 military time, that would be 1 o'clock in the afternoon. Add 4 to that, and we would be in Zulu time. So 13 plus 4, 1,700 Zulu is 1 o'clock in the afternoon. Now 1843 add 4, 19, 20, 21, 22, it's 23, 22, whatever the time was. Yeah, 22. So that's what Zulu time is. When you're reading certain types of weather information, they'll report it at this Zulu time. These were the conditions. And so that's how you're going to do the conversion. It's again, take the local time, convert it to military time, add 4 hours if you're in daylight savings time, add 5 hours if you're in standard time. If you're in the central United States, it'd be add 5 or add 6. If you're on this mountain time, it'd be 7 or 8, and then if it's West Coast, 8 or 9. Okay. So your aviation operating time is expressed in terms of the 24-hour clock. For example, 8 o'clock a.m. and 2 p.m. is 1400 local. Why do I have 8 a.m. is 8? I don't know what the heck I did there. I think I can show you a couple examples. Yeah, often represented by universal time, UTC or GMT time. 2 p.m. is 1400 local. On Eastern Daylight Savings Time, that would be the equivalent of 1800 Zulu. So 1400 plus the 400 that I talked about gives you 1800 Zulu. All right, mentioned at the beginning quite a couple times here, we've got the true North Pole and we've got the magnetic North Pole. They're not coincident on top of each other. And you notice these kind of curved lines. These are called isogonic and agonic lines. And in each of these lines represents some level of variation, of magnetic variation associated with the magnetic North Pole. The North Magnetic Pole is about 71 degrees north latitude and 96 degrees west longitude, and is about 1,300 nautical miles away from the true North Pole. I think the last point is all really need to highlight here. It's quite a ways different, and it does vary based on the magnetic core of the Earth, or the molten metal in the center of the Earth. It does change over time. It changes so much that sometimes they have to rename the runways. Instead of runway 26, they might change it to a 25 or 27 over some decade of time. They do it at times. The Earth is not uniformly magnetized. As a result, in the USA, compass needle usually points in general direction of the magnetic North Pole, but may vary in certain geographical locations by many degrees. For example, here, where we are, it's somewhere around 15 degrees. This must be an old picture because it's more about plus 15 now, not the plus 20 that you kind of see right here in New Hampshire. It's actually shifted. They basically have thousands of monitors around the Earth or magnetic sensors, and they wind up, based on that, drawing these lines. And one's called the agonic line, where they call it 0 lines of magnetic variation, and then it's to the right of it, it's plus, and to the left of it, it's negative. And we'll factor that in our flight plan when we do our cross-country flight planning. And again, they're called isogonic lines, and the main 0 one is called the agonic line. There are sometimes you don't see in this picture, but there can be some twists and turns in this a little bit based on certain types of geological material in the Earth. Maybe there's more metal or iron ore in certain regions. That could cause you to have a little bit of a blip. And by the way, Brian, you can see my screen here, all my presentations. Is that correct?
Yep.
Okay. So the isogonic line is represented on the sectional by this thick magenta line running from the northwest to the southeast. Here you see it says 15 degrees west. And we factor that in when we're doing our planning for our cross-country flight. The other type of thing that we have to factor in is the compass deviation. Again, the compass may not read accurately because of its installation in the aircraft. There could be radio frequencies could be affecting it. Metal could be affecting it inside the aircraft. And it's basically known as deviation. It's magnetic compass deviation. So you have to factor that in when you're flying. For example, if you look at this little sheet that's next to the compass, and every plane has to have it in it, if it said, if you want to fly a heading of 60 degrees, steer something or other, a mechanic would go out and he does a calibration, and it might say, if you want to fly 60, steer 62. So you know you have to add basically two degrees to your calculations when you're flying. So we've done wind correction from the true course. We've done magnetic variation because of those isogonic lines, and then we would factor in compass deviation by looking at this card. Compensation for the effects of wind is a major part of pilotage and dead reckoning and flight planning. So we're going to get into a few pictures on this. Wind direction report is the direction from which the wind blows. So if the wind's coming from the northwest, the wind's, let's say, northwest, it's blowing from the northwest going to the southeast. Downwind is moving with the wind. Upwind is moving against the wind, going into the current of airflow. Cross winds are basically, if you're going, let's say, north to south and the wind's blowing from the west to the east, that's a crosswind. The path of an aircraft is a combination of both the aircraft's movement through the air and by the motion of the air on the Earth's surface. And so here you see in figure 1, plane is at point A, wants to go to point B, but there's a strong crosswind. And if he does nothing, he's just going to basically be driven off course and not make it to point B. Yep, so that picture B basically shows that. His desired destination was due north, but he winds up drifting off actually to the northeast because he hasn't done anything about the wind. So the solution that he's got to crab into the wind, he's got to turn the plane to a heading so that he will go from point A to point B. So he may be steering somewhere to the northwest just to go to the north because of the strong westerly winds. All right, so we can determine how much wind correction we need by looking at this thing called the whiz wheel on the back, the Z6B computer, and this is the whiz wheel. It spins around like this, okay? And you can move it up and down. That's a picture of it. And from it, we can find not only the wind correction angle, but we can also find out what our effective ground speed is. We know our true airspeed flying through the air at a certain altitude. Well, we need to know based on the wind what our actual ground speed is. And again, this side of this E6B is what we use. We can also find the pressure altitude and density altitude on this side, on the back side of the chart. And we can also find, using the back side of the chart, the true airspeed. We can find distance. We can find fuel flow. Basically, we can do basically any type of math that we need on this little toy here, our computer. So we're going to show you, I think, here on wind correctional angle and how we've used the whiz wheel to make that happen. So I'm going to try to get here quickly to show you this video on that. So this is wind correction angle. Oh, did I put the whole video on? Let me just see if I'm going to review an example of 6 degrees. Okay, let's see if I'm successful. Brian, you still there?
Yes, sir, I am.
All right, I got a weird pop-up that showed up. So
I see my initials are gone.
it says Brian Post unverified.
Well, I don't know who unverified me.
Yeah, neither do I. So let's see if I can get to this link here and get successful. All right, now I got to figure it out. This takes me a minute. Automatic. How do you turn off a pointer? Maybe I do that. There we go.
I just know that from the moment that I got involved with Republic, I didn't just feel like a number. I felt like I was being invested in.
Well, I didn't put the time in. So follow on. In this exercise, as part of cross-country flight planning from Laconia Airport to Auburn Lewiston, Maine, we're going to determine our course heading to actually fly. This is what we would see on the directional gyro or heading indicators. So again, what we're going to do is determine the wind correction error that we have to factor in for this trip at cruise altitude of 5,500. So all we have to do is use the E6B whiz wheel instructions that are very well spelled out right up here at the top. The first thing it asks us to do is set the wind direction under the true index. I have already gone ahead and I've set the wind direction, which is 280, underneath the true index. I just want to pause for a second. So as part of this exercise, you need to know what the winds are en route. And so you can, it's hidden behind the C6B, but we found the winds at the surface leaving Laconia. We found the winds aloft like 6,000 feet. not only the wind direction, but the wind velocity and the wind temperature. Okay, and now with that information, I'm showing you how to find the wind correction angle and your ground speed. Then it says mark the wind velocity up from the center point. This is our center point. Also, I call it a grommet. I'm going to set my wind correction grommet center point at the 100 mark because it's easier to make estimates on the marks using that as a common reference point. The wind was 17 knots, so I'm going to go up here. There's 10, there's 20, so I'm going to make a mark at 17 on the whiz wheel. All right, now that I've established my mark, the next instruction is set the true course under the true index. The true course here is 59 degrees. And there it is. There's my 59 degrees. And the next requirement is slide the wind velocity mark that we made to the true airspeed. Well, the true airspeed we said was 110 knots at our cruise. So we have our mark at the 110 knot line here on the whiz wheel. Now, the first thing we want to note is what is your ground speed? Ground speed reads underneath the center point or grommet. So it looks like it's about 121 knots ground speed. We'll make a note of that on our chart. And we'll go ahead and we'll just put that right here. It's going to be that number 121 knots for the duration of the flight. So next we need to account for the error associated with the wind correction. So we look at the center line here and we count 2, 4, about 6 degrees left of the center line. And we're going to put that 6 degrees right here in the chart. And as you can see here, the mark is to the left of the center line. So we're going to put a minus sign here. As indicated here, minus if it's on the left, plus if it's on the right. We'll subtract that out, and we get 53. So I just wanted to highlight here, this was when we departed the airport. Here's our en route phase at 5,500 feet. This was the wind direction, the velocity, and the temperature. And we used the whiz wheel to determine what type of wind correction angle we needed to have in here. We took the true course 59, subtracted the 6, and we get 53. And we figured out the ground speed as well as part of this exercise. Okay. See what else it says here. I think it's the magnetic variation next. And so now that we've compensated our course heading for wind correction, we now need to determine the amount of magnetic variation we have to deal with. This is our route from Laconia Airport to Auburn-Lewiston in ForeFlight. What I'm looking for is that magenta line right there, this magenta dashed line. This is an isogonic line. And I'm going to go up here to see a number here. There I do. I see 15 degrees west. So we're going to add that 15 degrees or subtract. We need to determine first here. We're going to put that 15 degrees in the table right here. So it said west, so we're going to add plus 15. So that gives us 63. That gives us 68. By the way, it doesn't matter which direction we're going here. If it was 15 west, we're going to always add 15, plus 15. Whether we're going from Auburn-Lewiston in this direction or we're going from Auburn-Lewiston back down to Laconia, it's plus 15. Okay, so accounting for magnetic lines of variation, we have a magnetic heading of 68 degrees. Now the last thing we have to look at is what is our compass deviation. We can check out our compass deviation errors by looking at the deviation card associated with the compass. I know in the case for the compass that we're using in our aircraft and the heading that we're roughly on, it's about 2 degrees. So we're going to put plus 2, and this means we're going to fly a heading, a course heading in the end, of 70. And that is the heading, the course heading that we're actually going to fly when in the aircraft in steering toward Auburn Lewiston. We're going to actually show a 7-0. All right, so that's pretty much that portion. What's that, Mike? All right, let me get back to the presentation. Let's see if I can get back down to this. And all right, so that's what we were doing here, basically how to find wind correction, how to calculate the ground speed, and that's pretty much all I want to show on that. The next thing is about pressure altitude and density altitude. I told you earlier, we need to know what the pressure altitude we're flying in, the density altitude to know how the aircraft's going to perform. So again, we're going to go to this little video here, and we'll show something on that.
Guess I won't be making my famous burgers.
Text everyone to cancel. I bet this is.
Based on the METAR, is looking at the two windows we care about. Field elevation is 11 in E6B. How we can determine what the pressure altitude is at our departing or arriving airport. So for this example, in calculating the pressure altitude using an E6B flight computer, we're going to use this METAR that comes out of Phoenix, Sky Harbor Airport. And what we can see here is the temperature is 7 degrees Celsius, and the density altitude reads 266 feet. And we know the field elevation is 1,135 feet. So we're going to go ahead and determine the pressure altitude using the E6B based on this data from the METAR. So the two windows we care about for determining pressure altitude for this question on what the pressure altitude is at Sky Harbor Airport in Phoenix at this moment, based on the METAR, is looking at the pressure altitude window and the density altitude window, as well as the temperature scale across the top of the pressure altitude window. So we were told that the density altitude at Sky Harbor at that time was about 266 feet. So there's 1,000 foot. There's about 500 feet. And I'm going to say somewhere right about there is about 266 feet. Really fine grain there. So then we take a look at what the temperature scale showed. There's 0 degrees Celsius, 10, 20, 30, 40, 50. We care about 7 degrees Celsius. So if that's 0, that's 5, and that's 10, it looks like it's right about 1,000 feet, maybe just shy of 1,000 feet pressure altitude. Well, how does that E6B determination of pressure altitude equate to the mathematical way for figuring out the pressure altitude? Well, we have a field elevation Phoenix at 1135, temp again 7 degrees Celsius, altimeter 30.14 inches, density altitude 266. In order to calculate pressure altitude, we need to take the difference between the standard pressure and the current barometric pressure reading. So 30.14 minus 29.92 equals 0.22. We're going to multiply that by 1,000. We need to do something with this 220 feet. Well, since the altimeter is reading heavier or higher number than the standard pressure of 29.92, we're going to wind up subtracting that 220 from the 1135 field elevation, and works out to 915 feet. So indeed, what we determined on the E6B for pressure altitude was correct. We roughly saw just under 1,000 for pressure altitude on the E6B, and we calculated here 915 feet. All right, so that is how we get pressure altitude, density altitude. You can do it the old mathematical way. There's tools called e6bx.com. You can go there and you can just type in the airport and they'll give you that information. But I guarantee you, you're going to be asked questions like that on an oral exam. I had a student just here earlier today, had an oral exam, and it didn't go well for him. And one of the areas, though, he did do right was he was able to calculate the pressure altitude in front of the examiner. So I was happy that that one part of it went well. Again, so we just went through that, finding time, distance, and true airspeed with the E6B. So now we're going to use the same tool to know, to be able to calculate time it's going to take. We know our distance between points. Matter of fact, I'll highlight again if you see it on the picture or video in a second. We know our distance between points, and we know our ground speed, and so we can calculate time. And we could sit there with a paper and pencil and just do the math here, but we can also use this and do it very quickly. So I'm going to show you that one next. I struggle to find my cursor. There it is. Oh, and I forgot to see what time was at. Did it say what? Do you guys remember what time it was?
Unlock incredible deals and explore the best selection of musical equipment at Sweetwater. From stage to
that we can get the pressure altitude. The first way that you can get the pressure altitude is if you're sitting in the plane, is just dial up 29.92 inches of mercury in the Colsman window on the altimeter and just read what the altimeter.
What's that?
Alt. Let you switch.
Let's look at how to use the circular slide rule. You'll see a ring of numbers on the static outer scale, along with a separate set of numbers on the movable inner scale. There are also two important pointers to take note of. The black 10 on the outer scale and the black 60 rate pointer on the inner scale, which we'll be referring to frequently when working through sample calculations. As a general rule of thumb, the 10 pointer will be referenced when performing basic math problems, and the 60 rate pointer will be used when computing problems related to time, like miles per hour or gallons per hour. One thing to remember is that most slide rules, including the E6B, do not account for orders of magnitude. This means the numbers on any of the scales could represent any variation of that number. The number 30, for example, could represent 0.3, 3, 30, 300, or 3,000, depending on the context of the problem and inputs you're using. It might sound confusing now, but it'll make sense once we start looking at specific examples. To get a feel for the operation of the slide rule, let's show how to do a basic multiplication problem. Let's say you wanted to multiply 5 by 7. Find the number 50 on the inner scale, which represents 5 for this example, and line it up with the black 10 pointer at the top. Now, find the second number, 70, on the outer scale, which represents 7, and read the number across from it on the inner scale, 35. To help illustrate the order of magnitude concept, you can also use this same...
Oh, God. Okay, so let's see. So this one is on finding time distance with E6B. Okay, let me just get to that. It's 120. I know which one that is. So I'll go back to my channel. Welcome to Falcon Imagery. E6B.
If you're taking a trip with your friends,
have you ever heard of an economy being taxed into prosperity?
Speed. We need to determine what the time and route is. We've got our distance and we've got our ground speed. And the ground speeds that we've calculated, we can use our E6B to determine what the time is between the legs along the route. So the first thing I want you to do is to look at this set of instructions here. We want to put the triangle underneath our ground speed. And with that, we can then look on the outer ring to determine the distance of the leg that we're flying to determine our time and route between legs. So in this scenario, we are flying 121 knots ground speed. So we're going to put the arrow under 121 knots right there. So without moving the whiz wheel such that our triangle stays underneath the 121 knots, we're going to go look at the number 40, or in this case, really 4 nautical miles. And we look down at the middle set of numbers here, the inner arc of numbers, and we see 2. So we know it's not going to take us, or we see 20. We know it's not going to take us 20 minutes to go 4 nautical miles at 121 knots. It's going to take us 2 minutes. And so we're going to record 2 minutes right in here on our
via our navigation log. Then the next leg is 15 nautical miles. So we're going to, again, while maintaining the triangle underneath the ground speed of 121 knots, we're just going to move this and look at the outer ring for 15 nautical miles and see what we see for time underneath. 70, 80, we know it's not 70 or 80 minutes, it's going to be between 7 and 8 minutes, or roughly 7.5 minutes. So we're going to record that time. Next, we're going to look at the number 12 and see that it's showing the 60 underneath it. And so we know it's going to take approximately 6 minutes to go the 12 miles. So put the 6 in here. And then lastly, we have 10 nautical miles. We look at the 10, we look underneath. It looks like it'll take us about 5 minutes. So we'll add these times up and we'll know what our total length of time is for this trip. So the total length and time to go from Laconia to Auburn, Lewiston, Maine, based on these wind conditions and flying at 121 ground speed, plus the 79 ground speed for the initial top of climb, works up to 32.5 minutes. So that's all there is to it, to using an E6B whiz wheel for estimating time and route between waypoints on a cross-country flight plan. Once you know the ground speed, all you do is set the triangle up underneath the ground speed, which is on the outer ring of the E6B, and then just pick off the points. You look at the outer ring for the distances you're going to travel between the waypoints, and the middle ring you're going to look, or the inner ring, you're going to look to determine the estimated time and route between those. Okay. And then you said all Windows tab. Okay, good. All right, so that's basically how we find our distance. And the last part of this is finding the fuel burn. Let's see if this one will work here. Click on that.
Athletes everywhere, including myself, swear by this. It's better, it works, and I'll tell you why. You may already know.
Welcome to Falcon Imagery. Fuel burn. There it is. Do that. We have our E6B whiz wheel. What we want to look for is this bottom set of instructions where it says we've got a triangle here. We want to put the triangle underneath the gallons per hour burn rate that we're going to burn. In this case, we're going to be burning 8.5 gallons per hour in cruise. And then we look at our estimated time and route by looking at the inner or the middle set of numbers, and then going up to the outer ring to determine the number of gallons we're going to burn along that leg of the cross-country flight. So let's put this into use. So again, guys, we've found our ground speed, we've got our distance between points, we've figured out time, we know what our fuel burn is in cruise, and now we're trying to figure out our fuel consumption on each leg of this trip. So using the whiz wheel, I'm going to put the triangle underneath the 8.5 gallons per hour fuel burn. Then while holding that fixed with my fingers and thumb, I'm going to look for the amount of time on this inner ring that I anticipate flying for the first leg, which was 2 minutes, as shown in the VR navigation log. So I go to the inner ring and I look for 2 minutes, and I see it right there, and I go up. So I know I'm not going to be burning 3 gallons or 2.5 gallons, something in between, but it's not gallons, it's going to be tenths of gallons. You just kind of have to look at the numbers to see that they make logical sense. If I'm going to only fly for 2 minutes, I'm going to be burning, it looks like, approximately just under 0.3 gallons of fuel. So I'm going to round up and just call it a whole 0.3 gallons of fuel to fly those 2 minutes. And I'll put that in my log. Next, I'm going to fly 7.5 minutes. So I'm going to go again on the inner wheel and looking for 7.5 minutes. There's 7.5 minutes. I'm going to come up here and I'm going to see that I'm going to burn, it looks like about 1 gallon to maybe 1.1 gallon of fuel over that 7.5 minute period. So I'm going to be, again, conservative here, because it's 7.5 minutes. I'm going to be conservative and go 1.1 gallons. Next, I have to look for 6 minutes. Well, 6 minutes, there's the 6 minutes. Right here in this inner curve, it comes up to, again, the 8.5. Well, I know I'm not burning 885. Okay. Then tab, go back to the presentation. And that's basically what we use to get all of our fuel burn for that trip. So now we're going to leave all those videos and go right back into some other just slides here. We're going to talk about diversions to alternate airports. I already mentioned to you today that I had a situation where there's a lot of heavy rain coming down here. So we put ourselves out towards Sanford, the seacoast, Sanford, Maine. So we had a diversion we needed to get down and out of the bad weather. Similarly, when you're picking your route across flight, you're paying attention where you can divert to along the way. Here's Portland, Maine, would have been an easy one to go to on our way from here to Auburn, Lewiston, Maine. So diversions might happen because you have low fuel, you got bad weather, you're tired, you're sick all of a sudden, your passenger got sick, or there's something wrong in the plane. Like it might not be an engine problem, but you may have a failed alternator and you're running off the battery and going to lose your avionics soon. So you might have that for a reason to divert. When you do decide to divert, confirm where you are. Take a look on your sectional map, look outside, you go, yeah, I'm here. If you can use your GPS avionics and put an alternate airport in, go ahead and put the nearest airport and go to. Estimate a heading that you'll fly. You can either estimate it based on looking at the sectional, or the GPS will tell you which way to turn the plane. And you just fly there. Note the time that you left your spot and the heading you turn to. And then if you can, draw it out. Again, with the GPS avionics today, it does it for you. It puts a little pretty magenta line and you fly the magenta line. Again, if your GPS is equipped with nearest page, you click on nearest, find an airport that's nearest to you, select it, and then hit go or activate, and it'll send you right to there. The next thing is lost aircraft procedures. This is too much slide of mine. Let me just. Brian, are you seeing a big thing in the middle of your screen?
What's that?
Are you seeing anything in your screen when I present? Okay, never mind.
Just a lost aircraft, just 5C, yep.
All right, for whatever reason, the little box here keeps popping up in the middle of the screen down below. Not a problem. All right, so if you're lost, there's something called the 5 Cs. All right, if you get lost, you don't know where you are, the first thing you want to do is climb. The higher you go, the better you're going to see. Around here, you get up around 3,000 feet, you can see the Atlantic Ocean. You know that's the Atlantic Ocean, you know that's the east. Okay, that'll be a good sign. If you get high enough, you'll see Boston as well. So first of all, climb if you get lost or confused where you're at. Ceiling and visibility permitting. I mean, you can't go up in the clouds. That's not going to help you to find out where you are. Not to mention, it'll probably get yourself killed. The other advantage of climbing, the higher you go up, you'll have better line of sight with radio frequencies on the ground. So you'll be able to pick up other airports nearby or further away, even the higher up you go in altitude.
Do you continue on the course heading that you're on, or do you just, guess what, I'm not, circle and go up?
That's my next point. Okay, so what the heck's going on? Why am I not being able to accelerate through this? There's always something here. All right, that's the next part.
There we go.
There we go. I don't know what that's going on. All right, conserve. Be sure not to fly around aimlessly. Circle. Usually you get in altitude and you kind of stay in just general radius around the area. Just don't go aimlessly off in one direction, not even paying attention where you're going. Circle. Operate aircraft at maximum endurance power speed. What does that mean? Don't sit there and get nervous and put full throttle in and ripping it and going really fast in circles. Just get this thing on a very low cruise power setting. Take, wide circling turns to orientate yourself, to get a little sense of what direction, where maybe the Atlantic Ocean is, etc. And check your fuel state and kind of assess how long you've got for state circling above. Communicate. So you've climbed, you've conserved, you got better radio reception now, communicate. There's plenty of frequencies you can reach out to, but one of the best ones is 121.5. You dial into that frequency, you tell them you're lost,
And you can also squawk 7700 too, if you've got a communication issues. But in general, you just tell them, hey, I'm lost. That's the confess part. So get the rate frequency, confess that you're lost, and then when they tell you to turn to a certain heading, you do it. You comply. You go to that way. So those are your 5 C's. See and avoid. As a VFR pilot, we are required to be looking out that window most of the time, like 90% of the time. We don't want students or pilots sitting there like this, looking at their iPad or looking down at their avionics nonstop and never looking outside and they're looking for that plane that's close by. Next thing you know, it's hit them in the face, literally, by spending too much time down. So the FAA is pretty strict on this one. When there's visual flight rules, you're expected to be seeing and avoiding. Only if you're an IFR plane, an IFR rated pilot flying an IFR flight, can you be sitting there and relying on air traffic control to keep you out of the clouds. Relies on knowledge and limitations of human eye and proper scanning techniques. Yeah, so we'll talk about scanning techniques too here in a second. So stay alert. When you're scanning, you're kind of going from a left to a right. Usually you look out far and then you kind of work your way in. Instruments left to right, then scan left to right. Yeah. Couple things here. So aircraft on the rise with no relative movement. If you see an airplane out there and it's just stationary in front of you, it's just, maybe it's at night too, it's just a dot. If it's not moving, it's either coming at you or going away from you. If the light's getting brighter, it's coming at you. And so you're going to want to go off to the right. When aircraft are coming right at each other, they each both go to the right. Yeah, if increasing size, take immediate action. Again, 80% outside, 20% inside. Announce your position on the common traffic advisory frequency. Frequently, we're doing maneuvers out here. We'll let people know where we are. Hey, we're 5 miles to the north, 3,000 feet doing maneuvers. Especially, we'll say that when we hear people, let's say they're departed with a right turn out to the north, and we can see them on our ADSB, and we know they're climbing in our direction. We'll just say, hey, announcing we're out here for 3,000 feet, 5 miles north airport maneuvering. Again, look from right to left or left to right. Better to look out far and then come back in and look closer and closer. For each stop, an area approximately 30 degrees wide should be scanned. So you take a view of about 30 degrees, then you turn to the right a little bit, and you overlap, I think, by 10 degrees, and spend 2 or 3 seconds in each scan section before you turn, just to allow your eyes to have a chance to focus. This is a big problem, particularly in general aviation at airports like Laconia, where you may have a low wing plane like our Piper Warriors and a high wing plane like this Skyhawk here. They can't see each other. I actually had a very close call back when I was getting my private pilot's license, where I entered the pattern coming in from across country, and the next thing I know, a Warrior came down right in front of me, maybe 200 yards away from me, in front of me. And I said, Jesus, he didn't make his call. Well, he made his call, but I thought he was behind me. Next thing he fell right in front of me. So I immediately did a 360, came around to give separation. And why? I'm sitting there in a Cessna Skyhawk at the time. I can't see above me. And he's in a low wing plane. He can't see below him. And he said he was on the 45 entry. I said I was on the 45. But at that time, we didn't have ADSB, so he had no idea how close we were until literally came down right in front of me. That was a close call. Situations involving greatest risk, local practice area, like around here, it's over the lake. Over VORs, VHF, omnidirectional range radio, we can talk about that shortly. But basically, there's a lot of traffic flying over those for navigation purposes, but also for training purposes. Again, any airport usually busier. Traffic patterns are very busy, and very common flight paths, which are something called associated VORs. We'll get into them. I don't know tonight, but I might show them. Use of flight following en route. So one of the big things, as a matter of fact, I just came out with a video yesterday on this, use of VFR flight following and use of VFR flight plans. So VFR flight following is when we leave this airport on a cross-country flight, we'll switch to air traffic control and say, hey, look, we just left Laconia. We're going up to Harbor Lewiston. We're currently passing through, let's say, 2,000 feet to 5,500, and we'd like to pick up flight following. and ATC would say, okay, we want you to squawk this code. And instead of a number 1200, which we normally see, we'll put in whatever the code they give us. They might also ask us to ident, and we blow up as a little red button or a little red light on their radar screen. And that lets them know, okay, yep, we see you, and we see at this altitude. And now they're an extra set of eyes. But you're flying up there alone on your flight, cross-country flight, they're seeing you. And they might say, hey, 4050 Bravo, you got traffic 12 o'clock at your altitude. And it's like, oh, okay, well, there's a plane coming right at me. I better be paying attention for it. In some cases, they might say, hey, 4050 Bravo, turn right immediately to 090 to avoid the traffic. But the big point is they're an advisory service that air traffic control provides to keep you safe. So if you're foolish, if you don't take advantage of this free service, it's easy to use. Airspace. Next thing is just an airspace. I think we've already covered airspace, but I just want to reiterate again. When you're flying between 18,000 and 60,000 feet, or flight level 60, your IFR conditions, you guys as private pilots only wouldn't be in this space. But if you get your instrument rating, you have a full access to that space. Class Golf is where we're at today. We're sitting here at Class Golf airspace. That's from the ground up to 700 feet or 1,200 feet, in rare cases up to 14,500. Above the Class Golf is Class Echo airspace. That is controlled airspace as well. And you don't need to be talking to air traffic control, but it is considered controlled space. The only uncontrolled space where ATC doesn't talk to you is here in Class G. Class Bravo represents like the Logans, Boston. Class Charlie would represent like Manchester or Portland, Maine, and Class Delta would represent Pease Portsmouth Airport or Lebanon Airport, around this vicinity. And then we have all these separate flight visibility and distance from clouds that we have to care about. Class A, you guys don't have to care about because it's IFR, it's 18,000 feet. Private pilot, you don't have to worry about it. Class Bravo, that's, let's say you were down at Logan, you need to be 3 statute miles visibility and clear the clouds. Class Charlie and Delta and Echo up to 10,000 feet, you need 3 statute miles, and you need to be either 500 feet below the clouds or 1,000 feet above them and 2,000 feet horizontally away from them. Above 10,000 feet Class Echo, you need 5 statute miles, 1,000 feet above, 1,000 feet below, and then 1 statute miles horizontally. Any idea why you need more separation at 10,000 feet or above? Any ideas? Any ideas, Mike?
Airplanes are faster.
That's right. Above 10,000 feet, they can fly above 250 knots. So we want to give ourselves a little bit more visibility and distance from mountain clouds. So we might have a chance as a pilot to see the other aircraft coming at us.
Those speed limits, are they indicated airspeed?
Yes, indicated airspeed. Yep. Class Golf is complicated. So we'll put it in perspective. For daytime use, and less than 1,200 feet above the ground, only 1 statute mile clear clouds. Once you get above 1,200 feet, you need 1 statute mile and the 152 rule, just like you had with Class Charlie, Delta, and Echo. At night, they want that extra visibility, 3 statute miles, and again, the 152 rule. And then if you're, let's say, on an airport that's, let's say, on Pikes Peak, you know, really tall mountain, and then you go off of it, and you're more than 1,200 feet above the top of that mountain, and now you go off the side of that mountain, and you're like 14,000 feet up in the air, MSL above sea level, they want that 5 statute miles rule. Why? Because you're now in that zone where the aircraft can be going a lot faster. This slide I have to fix a little bit. So when we're in these planes, as I said, VFR flight following, I said the air traffic control, we might want you to squawk some code. Well, what we mean by squawk, there's a transponder inside the airplane that sends out a signal with information about the aircraft's tail number, its speed, its position, information, and usually a couple other things. And air traffic control wants to know that so they can be able to keep you separated from other traffic. So we need a mode C transponder, which gives you that type of information I just mentioned, and something called ADSB out. And then depending what type of airspace you're in, you may need certain types of communications. I'm not going to go through this whole chart, but suffice it to say, you need a mode C transponder in class Alpha, way up high at 18,000 feet, class Bravo in Logan, airport type things, at class Charlie, Manchester Airport. You don't need it in a class D airspace. You do need a class Echo when you're 10,000 feet up. Again, you're in the realm where planes are going really fast, so they want to be able to see you and identify you. And it's similar to class Golf. It's class Golf is uncontrolled, but when you get up into those few places where it's class Golf up to 14,500, as long as if you're over 10,000 feet, you need to have that ADSB out and mode C transponder working. So that is pretty much it for tonight, I believe. Yeah, that is pretty much it for this evening. Any specific questions on that? Let me just go back a few slides. I want to see if there's something I missed here. If there's something that's pretty much it for this evening. Any questions, guys? All right, well, I've basically given you a good foundation for Monday's class, next Monday's class, which is please come with your E6B, your plotters, your sectional charts. You're going to have them all stretched out here, and you're going to be filling out one of those nav logs by hand for another trip up to Arlington. And it's kind of a working session. So you're going to be bring pencils if you can, because you're going to be writing on your sectional chart. Any questions? All right, we'll see you again next Monday. I'll be teaching it, and Thomas will be your Wednesday.
Thank you.
All right.